All right, well, welcome back everyone, and we'll take a look now in this video at dye-substituted cyclohexane systems and the influence the two substituents have on the population of the two chair conformations. So we saw in the previous video about how the influence of a single substituent would have on the equilibrium distribution of the two chair conformations in cases like the T-butyl group would strongly bias that chair towards the one of the two possible conformations. What we want to look at here is what the influence would be of putting more than one substituent on a cyclohexane chair. And so we'll take a look at some examples of this. And so we'll start by drawing the molecule that we want to take a look at, just in our usual flat representation. So here I'll put a methyl group. So I'll put two methyl groups. Both of them are sticking out of the plane of the page towards us, although we'll see in a minute, doesn't really matter. Sticking out of the plane of the page towards us in this particular molecule. And so the name of this particular molecule, just a little brief instance of nomenclature here, is called cis. So that's kind of all crammed on the side of the screen there. Cis 1,4-dimethyl cyclohexane. And the only point on nomenclature I'm going to make here is that this is the only instance where we use the phrase cis and trans. And in another video early next week, we'll talk a little bit about E versus Z. But cis and trans is the only occasion where we use this in reference to the orientation of substituents on cycloalkanes in particular, cyclic molecules, cycloalkanes. And so here cis implies that both of the substituents, in this case the two methyl groups, are on the same side of that aromatic ring. So cis 1,4-dimethyl cyclohexane. Okay, so now let's take a look at the chair conformations of this particular molecule. So I'll just draw out a chair here. Draw out a chair here, and again what I like to do if I don't know where I need to put anything is I'll start perhaps just by sticking one of those methyls on one of the carbon atoms, in this case in an equatorial position here. So CH3 sticking out there. Now where else? No, the other substituent is the methyl group on the fourth carbon atom. So if this is, if the carbon atom, if this is 1 here, 2, 3, 4 over there is where the other methyl is going to go. So 4 carbons over. And it's got to go on the same side of the molecule. It's got to go on the same side of the molecule as the existing methyl group that's there. And if you can't see it on this, if you've got your model kit, you'd be able to see it, and I'll show you on the model kit in a second, try and convince you that both of these have to be sitting on the same side of the molecule. If the methyl that's equatorial is above the plane of the other carbon atoms, and the methyl that's axial on the other carbon is also above the plane of the other carbon atoms. Okay, and that's in equilibrium with another chair conformation. So let's take a look. And again, as we go from one chair conformation to the other chair conformation, what was the headrest goes down to become a new footrest, and what is the footrest goes up to become a new headrest. So let's see if we can draw that chair and then figure out where those substituents go. So there's a new chair. What was the footrest has become, headrest become the footrest, and what was the footrest has become the headrest. So now the substituent that's on the footrest here, this substituent here, that has now gone from an equatorial position to an axial position. And what was equatorial becomes axial in the new chair, and what was axial, which is this proton here, that was an axial hydrogen atom in the other chair conformation that we have, that's now become equatorial. And the substituent on that first chair conformation that was pointing up axial, that's now become equatorial. Sorry, I hit the edge of the screen here a little bit. That's become equatorial, and that proton that was equatorial has now become axial. Okay, so there was that chair and this chair here. So if you can't see that on the page, let me see if I can try and convince you of this with the model kit. Okay, so we've got the model of cis-1,4-dimethylcyclohexane shown here in the same kind of orientation that we initially drew it on the page, just lying flat. Those two methyl groups are sticking up, coming towards us. So there, if I've got it flat, you can see now if I turn it, those two methyl groups are sticking up. And what we want to do is make that chair conformation. So if you've got your model kit and you're able to kind of play along a little bit, make that first chair that we had, where we have now one of the methyl groups sticking out equatorial over here, and the other methyl group sticking up axial in this position. So that's the chair that we drew just a minute or two ago in the video. And now that's the model of that model kit. One is axial, one is equatorial. And now as I go from one chair to the other, what was equatorial becomes axial, and what was axial becomes equatorial. So again, I flopped through all of those conformations that Dr. Davis talked about a couple of videos ago. And now we've got the other chair conformation, where one substituent sticking up axial and the other one substituent sticking out equatorial. And again, we flop back and forth between the two chairs, one equatorial, one axial, one equatorial. So we go back and forth like this to the two different chairs. And we can see what we get here. So again, we started at this position with this particular methyl equatorial, this one axial, and back this way again. Okay, so that in itself is sort of interesting, but more usefully to us as chemists, trying to understand what's going on, let's look at what the energy difference is. Let's look at what the energy difference is between those two available chair conformations. So we started with this chair conformation where we've got one methyl group equatorial and another methyl group axial. And if we compare that just on paper or on the model kit, if you've got it handy, with the other conformation that we can draw, one sticking up axial, one equatorial, what we see, and again, we're focusing on these 1,3 diaxial interactions between the substituents that we have and the protons on the other side, or hydrogen atoms on the other side of the molecule. And what we observe here, for example, is that in this particular conformation that we have here, the only 1,3 diaxial interactions are between the methyl group and the protons with the red lines that we've indicated there. And in the other conformation, the only 1,3 diaxial interactions that we observe are between now this new axial methyl group and the hydrogen atoms on the other side of the ring, that 1,3 diaxial. And so if we flip back and forth between the two drawings, or if you flip back and forth between the two chair conformations that you can see, what you observe is there's really no difference between the interactions that we observe in these two chair conformations at all. Or more quantitatively, the predicted energy difference between these two chair conformations, that predicted energy difference there, if we express that as a delta G, that's 0. That energy difference, that delta G, would be 0. There's no difference, just like we had for cyclohexane, no difference in the interactions of the energies between these two conformations. Or, for example, if we wanted to think about the influence on an equilibrium constant, that equilibrium constant would be 1. And we will come back to this a bit more in Chapter 6 material, but I'll just kind of introduce it briefly here. Well, what about the other isomer of a 1,4-dimethylcyclohexane that we could imagine drawing? So I'll draw it out again, just kind of flat here. I'll leave this methyl group sticking up. And that methyl group pointing down at the bottom. And so this is trans. So it's trans 1,4-dimethylcyclohexane. Trans 1,4-dimethylcyclohexane is the name of that. Of course, trans implies the only place we use it is in disubstituted or in substituted alkanes, cycloalkanes, and trans applies that the two substituents are across the ring. Okay, and that's the only kind of little bit of nomenclature we'll do there. Again, what does this molecule look like? It's the chair conformations that we're really interested in. Again, I'll just stick one of the methyl groups out on the equatorial position here, just for the sake of drawing it in, and then try and figure out where the other methyl group goes on the other side. So again, that name implies trans. That name trans implies that those methyl groups are on opposite side or across that ring. And so if you're looking at it, if this methyl group in red here is sticking above the plane of the atoms, then the methyl group in green over here must be below the plane of the other atoms of the carbon ring. And if you can't see it on the drawing here, I'll see if I can convince you of that with the model kit in a second. What's the other chair conformation look like? Well, let's take a look. Equilibrium arrow, and again, we'll go from one chair to the other. This chair, what was the headrest, will now become the footrest, and what's the current footrest will turn into a headrest. So let's see if we can imagine what that chair might look like. So there's the chair itself. In this case, the red carbon atom here, that's equatorial. So we'll now have to put that axial. That's the one in red here. And this green methyl group over here, that's equatorial. So in our new chair, that's going to become axial, pointing straight down. And again, we can flip back and forth. Two equatorial substituents have now become axial in this new chair. Now I'll just kind of briefly take us through the model kit to see if you can follow along and just make sure that we can see those interactions more directly. So there's the 1,4-dimethyl cyclohexane sitting on the table as flat as I can get it with the model kit. This methyl group sticking up towards us. The other methyl group down here is sticking down away from us. And if I pick this up, here you can kind of see now, if I make the chair that we wanted to take a look at to start with, get my model kit in the right shape here. So we've got one methyl group sticking out equatorial, just as we started with the drawing we had a minute ago. One methyl group sticking out equatorial, and the other methyl group sticking out equatorial on the other side of the ring. And then as we flip from one chair to the other, the headrest will now become a new footrest, and this footrest will become a new headrest. So we flip across there to the other ring conformation that we have available, and now you see that the two substituents are sticking out axial with respect to each other. One of the methyl groups is sticking straight up, and the other one's sticking straight down in this particular conformation that we've drawn it. We've got, as again, we go from two equatorial substituents in one of the chairs to two axial substituents in the other chair. So the shape of that is fine, and the orientation of those two chairs is, with respect to each other, is interesting, but what we're really, again, interested in as chemists is what is the energy difference between these two chairs. So let's take a look at that. Okay, so let's start with this particular conformation, the one where the two methyl groups are sticking out equatorial. And so we said when we looked at singly substituted cyclohexanes that having that substituent stick out equatorial has no interactions with any other part of the molecule. And we observe the same thing here with disubstituted cyclohexanes, that those two methyl groups are sticking out in the equatorial position. There's nothing for them to interact on that molecule. So we would predict no diaxial interactions at all in this particular chair. But the other chair conformation, if we look at that, now we've got both of the substituents sticking up axial. So this methyl group on the top here would have 1,3 diaxial interactions with the hydrogen atoms in the positions that we've indicated with the red lines there, similar to what we are identical, in fact, what we were talking about with cyclohexane. And now underneath, or on the bottom side of the molecule, at least in the way we've drawn it in this case, we also get another set of 1,3 diaxial interactions underneath there that are nearly identical, in fact are identical to the ones we observe on the top. So what influence would this have on the distribution of these two chair conformations at equilibrium? We go from one chair where there's no interactions at all to another chair where there's two kinds of these interactions. Well, if you remember when we talked about methyl cyclohexane, that we said that difference in energy that these 1,3 diaxial interactions raise the energy of this conformation by 7.6 kilojoules per mole. And that kind of interaction is identical to what we're observing on the bottom half of this molecule, if you will. So that interaction there would also be expected to raise the energy of this conformation by 7.6 kilojoules per mole. And in fact, this is what we observe. We observe that this diaxial conformation, where both methyl groups are in the axial position, is 15.2 kilojoules per mole higher in energy than the other chair conformation where both of those methyl groups are sticking out equatorial. That's kind of a big energy difference in terms of what we're looking at here. What that means is that at equilibrium, 99.7% are in this equatorial, 99.7% of trans 1,4-dimethyl cyclohexane is in this di-equatorial conformation, equatorial conformation. That 15.6 kilojoules per mole is sufficient to ensure most of it sits in this conformation. And we'll see a couple of examples at the end of this video about how to use that information to kind of predict the energy of these interactions, to predict the chair conformation distribution at equilibrium. And then also at the very end of our time together in Chapter 7, we'll use this information to, again, predict outcomes of reactions and that involve looking at chair conformations. But for now, next what we'll take a look at is other patterns of substitution, so the 1,3 disubstituted cycloalkanes. So we'll start by taking a look at the cis isomer of 1,3 dimethyl cyclohexane. The cis isomer. I won't draw the whole word out. Cis 1,3 dimethyl cyclohexane, this disubstituted. Again, drawing it out flat like that doesn't tell us a whole heck of a lot, so we'll just draw the chair conformation, see if we can follow along about what we would expect to observe here. So again, I'll draw out the chair, I'll stick one of the methyl groups in that equatorial position just for a place to put it, and then try and figure out where I would expect to observe the other substituent in this particular instance. And so again, we're looking at the 1,3, so we've got the substituent here in this position, there's a carbon there, and then that other third position is over there, cis 1,3. So that's where we'd expect to observe the other substituent. So where do we place that on this chair? Well, we've got two places to put that substituent, and if the cis, the word cis implies that they're both on the same side of the ring. So in this instance, that means that the other substituent on that third carbon would also be on the equatorial position with a hydrogen atom down in the axial position there. And if you can't see this on the drawing, we'll take a look at the model in just a minute. I want to take a look at the other chair that we have access to here. So again, these are in equilibrium, and we'll be able to try and get a good estimate about how much to one side, to the right or the left of this arrow, these chairs lie on. I'll draw the other chair over here. And now again, and we're getting a little bit better at this, was the footrest becomes the headrest, and what was the headrest becomes the footrest. So there's the chair that we have, and we had the equatorial methyl group on the footrest, so now on the headrest, that becomes axial, and a hydrogen atom there. And on this other structure that we drew, this other conformation that we drew, the methyl group was sitting out equatorial, and the hydrogen atom was axial. So now we have this, where that's sitting up axial. The hydrogen atom is sitting equatorial position. Okay, And if you can't see that, or if you're still not convinced of this on the drawing, we'll take another look on the model kit just to make sure you can see what it is we're doing here. So on the table, we've got the model of the cis-1,3-dimethyl cyclohexane. Again, the two methyl groups are sticking up above the plane of the ring right towards our perspective. And we want to take a look at what the chair would look like. So I'll just flip it over. I'll put that one's first substituent equatorial. So the substituent on the bottom here is equatorial. And if you see, we've got the chair, the footrest, there's the headrest, and now that other red methyl group is sticking basically right at our perspective, looking straight at us, out in the equatorial position. And if I flip the chairs, now you can see that one of the, one of the molecules has gone, or one of the methyl groups has gone, both methyl groups have gone axial in that position. The new headrest, the new footrest, this methyl group is sticking up axial, and this methyl group is also sticking up axial there as well. So you can see that as we flip back and forth, both are equatorial, both are axial. Both equatorial, both axial. Again, if you're having a little trouble visualizing this, again, play around a little bit with the model kit. You should, if you've built the model kit correctly, you should be able to see exactly what's going on here. Now, of course, the key thing that we're really interested in as chemists is what's the energy difference between these conformations. So let's take a look at that. Well, we go from this conformation here where both substituents are equatorial. And so again, similar to what we just talked about for the 1,4 diaxial, we'd expect very little interaction or no interaction at all with the rest of the molecule. And the two substituents axial sticking up here, each one would be worth 7.6 kilojoules per mole. And there, 7.6 there. And again, in fact, that's exactly what we observe. .6 kilojoules per mole is that energy of interaction, again, biasing the whole thing to 99.7% to that equatorial conformation that we see here. Let's take a very quick look now that we're getting the hang of this. We'll do the trans 1,3-disubstituted cycloalkane, and then we'll look at a couple of examples that give us the opportunity to see how we make use of this information. Trans 1,3-dimethyl cyclohexane, and now we're getting a bit of the hang of this, so maybe we'll go through this a little bit quicker just to get a feel for what this might look like. Again, we'll draw a chair in here. I'll put that methyl group equatorial. And now if you've had some practice at this, you're probably drawing this out on your paper faster than I can do it over here. In the sense we've got the two substituents on this position 3, the third position, just a couple of atoms over from where we put the first substituent. One substituent's equatorial, one's axial, and if we're talking about trans or across the ring, then we can already see that that substituent would have to go axial. So we've got one substituent equatorial, one substituent axial. Well, let's take a look at what the other chair conformation looks like. And again, of course, these are in equilibrium, and we'll see in a minute or so just how far to the right or left this equilibrium arrow lies. And so again, we'll draw the chair conformation. The headrest becomes the footrest. Footrest becomes the headrest. That equatorial methyl now becomes axial. And that axial methyl now becomes, there's the hydrogen, that now becomes equatorial. So we go from one equatorial, one axial, to one equatorial and one axial. And so there's no difference in the interactions that we would predict for these chairs. We've got one 7.6 kilojoule per mole interaction over here in this particular conformation for this red methyl group, but in the other chair conformation we have that we observe, we see only that green methyl group has those 1,3-dioxyl interactions. So it's the same interaction here as we observe here. So the difference between these two conformations, the delta G naught, the difference is exactly 0. Difference is exactly 0. There's no difference in the energy, similar to what we observed for the 1,4. The other word that we often use for these is the word degenerate. Meaning that they're equal in energy. They're equal in energy. The two chairs are degenerate. They're completely equal in energy. So next, what we'll do is what I'll do is I'll show you on the model kit one last time just to make sure that you can see this for yourself as we go through the model kit, and then we'll look at a couple of examples. So now there we've got the 1,4-trans dimethyl cyclohexane on the table. We'll take a look at just very quickly to sort of make sure we can follow along between what we're drawing and what we observe in the model kit. One methyl sticking up towards us, one kind of going away from us, hard to see there. I've lifted up on its side. If I flip to the chair, you can see there we've got this methyl group sticking out equatorial, and this other red methyl group sticking down below the plane of the ring in that axial position. As I flip from one chair to the other, where the headrest becomes a new footrest, and that footrest becomes a new headrest, now we've got this methyl group sticking up axial, this methyl group sticking out equatorial here. Identical interactions in both sides. Identical interactions here and there. Those two chairs are degenerate with respect to the two chair conformations are degenerate or identical with respect to the energies. That one's sticking out, this one's axial. As I flip to the other chair, this one becomes axial, this one becomes equatorial. Identical energies in the chairs, delta G is 0. We call these degenerate or equal in energy. Next, we'll take a look at just a couple of quick examples to see how we make use of these kinds of interactions. So for example, we can imagine I'll put 3 substituents on a molecule and we'll just sort of see if we can get a feel for what the two chairs would look like, and then how we'd be able to predict what we would expect to observe for an energy difference between those chairs. Well, chlorine down here, I'll put a methyl over here, I'll put a hydroxyl group over here. And so what we're able to do is we're able to get all of these kinds of interactions that we've measured on a whole variety of molecules and use them to make these kind of predictions. Now, you're going to ask, where do I get these predictions from? The predictions come from this table here. You can call that up here. This table here, and this table is directly out of our textbook. That table is directly out of our textbook, and it's compiled by making observations on lots of substituents and trying to observe what the influence of those substituents is on the equilibrium between the two available chair conformations. Now, the other question you might be having is, hey, are we going to have to memorize these numbers? And the answer is no. We typically give these numbers in a data sheet that's available for you during the midterm and final exam. What we'd like you to be able to do is make use of these particular numbers in some way. And so again, this is the example that we'll take a look at here, is take a look at how we'd make use of that table to get a feel for what's happening with the substituents on this particular isomer here. So let's take a look at what we'd predict to observe for the chairs, and then kind of work backwards to see if we can deduce what the difference in energy might be. So there's one of the chairs, and I'll just put the substituents in. Again, we've got a methyl, a chlorine, and an OH substituent. And so here what I'll do is I'll put the methyl out in this position here. That axial. This is axial. And the OH sticking out in that direction there. And if I've drawn this correctly, then if the chlorine is on the opposite side of the ring from both the methyl and the hydroxyl group, if those are sticking out equatorial, that chlorine must be going up axial. And I'll leave it to you as an exercise to create this molecule with your model kit and convince yourself that what I've drawn here is a representation of one of the chairs that are available to that particular molecule. So now that we've got this, let's take a look at the other chair. Once you've got one chair, it's quite straightforward, I think, hopefully anyway, to deduce what the other one would look like. Right? The headrest becomes a footrest, the footrest becomes a headrest, and the substituents just follow along and where they're supposed to go. So now that chlorine was axial, it's now become equatorial, so that's a chlorine there, kind of right up against the edge of my screen. That methyl group that was equatorial has now become axial. The OH group that was axial has now become, or was equatorial, has now become axial. And I've drawn this in correctly. Those substituents are in the right place. One chlorine equatorial, an OH, and a CH3 that are in the axial position. And again, if you've got the model kit, you want to play along a little bit and draw and build it for yourself to see that I've drawn an accurate representation of this molecule. So now let's take a look and see if we can deduce what the interactions that we'd predict to observe here. And so again, we can go back to this table, and what we observe is that the 1,3 diaxial interactions that we'd expect to observe for the substituent where that chlorine is axial and the OH and the CH3 is equatorial, those interactions would be 2.0 kilojoules per mole. And the CH3 would be 0, and the OH would be 0 here. So the chlorine would be 0, the CH3 would be 0. I've drawn it in here. Chlorine, OH, methyl group is 0. So the total interaction that we'd expect for any kind of 1,3 diaxial interactions in this conformation is a total of 2 kilojoules per mole. That in and of itself doesn't tell us anything. We've got to compare that with the other conformation that we have access to. So this other conformation here, and again, if we go back to this table from the chapter 4, again, this is a table taken directly out of our textbook, out of chapter 4, and will be provided on the midterm and final exam in some fashion. That table tells us that, of course, the chlorine is equatorial, so the chlorine would be 0. The methyl group, 7.6 kilojoules per mole. We've seen that number a couple of times now. And this table tells us then that the OH group equals 4.2. Again, taken directly out of this table, so let's see what that looks like. I've drawn them in here. Chlorine is 0, methyl is 7.6, OH is 4.2. So the total interactions that we would expect to observe in this particular conformation, total interactions we expect to observe in this particular conformation is 11.8 kilojoules per mole. So 11.8 kilojoules per mole is a total interaction we'd expect to observe here. But the number that's the really critical one is the difference between this interaction here and this interaction here. So the overall delta G here would be predicted to be 11.8 kilojoules per mole. Or sorry, 9.8, excuse me. 9.8 kilojoules per mole. 11.8 minus 2. 9.8. That's the difference between those chair conformations. And so at equilibrium, that's about a 95% bias towards the more stable chair conformation, which is the one that's only got the chlorine substituent axial, as opposed to the one that's got the OH and the methyl group axial. And so there's an example of how we can use these numbers that are provided in that table 4.2 to predict some of the cyclohexane chair conformations and the difference of the two chairs. And so with that, that'll be the end of this particular video and the end of the cyclohexane chair conformations, and we'll move on to some new material with the next video that we post.